We're going to solve this problem using Ptolemy's theorem, which applies to cyclic quadrilaterals. If you have a cyclic quadrilateral, then the product of the diagonals is equal to the sum of the products of the opposite sides. In this case, d1 times d2 is equal to the sum of AC and BD. Let's do a brief proof before we solve the problem. Here we have cyclic quadrilateral ABCD, where the diagonals intersect at this point K. Take a look at the angles that cut off arc AD. These angles are angles ABD and angles ACD. Let's call that measure P. Now let's take a look at the inscribed angles that cut off arc AB. These are angle ADB and angle ACB. Let's call this angle Q. Finally, with arc BC, that's inscribed by angles BAC and angle BDC. Let's call it R. Finally, let's find a point E on diagonal AC such that angle EBC also equals P. Let's call angle BKE S. Let's find some similar triangles. Triangle EBC is similar to triangle ABD. So we have this ratio and we can solve for CE. We have another pair of similar triangles. Triangle ABE is similar to triangle CBK. So we have this relationship, and let's solve for AE. We have the diagonal of our quadrilateral AC is equal to AE plus CE. Let's start by taking the product of the diagonals and substituting. And our proof is complete. Let's take a look at isosceles trapezoids. All isosceles trapezoids are cyclic quadrilaterals. The two angles on top are congruent, and the two angles at the bottom, let's take a look at the angle sum. The sum of the angles is 360, so we have the opposite angles sum to 180 degrees. So all isosceles trapezoids are cyclic. We can see that they give us the height of triangle ABD, which is 10, but they also give us another height of this triangle. It turns out that AQ is also the height of the triangle from vertex D to side AB. You can see that more clearly here to the left. Then they also give us a third altitude of this triangle. If I extend the side AD past A and then draw a perpendicular from B to R, notice that this distance from B to R is the same as the distance from A to P because of the symmetry of our isosceles trapezoid. So AP is actually the height of our triangle ABD from vertex B to side AD. We can write the area of triangle ABD in terms of our three heights and our three side lengths. Multiplying by 2 and dividing by 90, we have this ratio. And we can write these side lengths BD, AB, and AD as 9x, 5x, and 6x respectively. Let's put these into the diagram. Now we can use Ptolemy's theorem on trapezoid ABCD. The diagonal has length 9x, so the square of 9x is equal to 5x times CD plus the two opposite side lengths, 6x times 6x. Solving for CD, we have CD is equal to 9x. We can look at our diagram here to figure out what DQ is. We just subtract 5x from 9x and divide by 2, and we get DQ is equal to 2x. Let's use the Pythagorean Theorem on triangle AQD to the left, which allows us to solve for x. So x is equal to 9 over 2 root 2. Let's solve for the area of our trapezoid in terms of x. It's the average of the bases multiplied by the height, which is 18. Rewriting in terms of x and substituting, we get our answer 567.